Hello, hello. Hi. All right, everybody. Change of variables, right? Jacobian, determinant, all that stuff. So what we're going to do here is a couple of examples, and we're going to move into chapter 13. So we went through that whole beautiful thing showing where the rho squared sine phi came from, right? From the conversion from Cartesian over to spherical coordinates, and that's where we ended class. But I had yet to give you an actual example of using change of variables. So here we go. We have our first example. Use the change of variables. So here you're given the change of variables. So as opposed to like a polar conversion, right, where you're given this idea of switching something. Well, let me back up. With the polar conversion, it's easy for me to show you visually what we're doing, right? But there's the change of variables. The idea of change of variables that you can change your variables x and y over to any other two variables, like in this case u and v, with any sort of conversion you want, so long as you can do the Jacobian, and so long as the new integral, the new region, is going to be something you can integrate. So I think that you'll see this play out when we actually do this example. Hopefully it'll start to make sense. Make that smaller. All right. So we've got our change of variable there. And we're trying to do this double integral over d of 4x plus 8y dA, where d is this parallelogram. So I'm going to start by drawing this region first. Right? I'm going to draw the region we're supposed to be integrating over. Try and draw it right here. All right. So it is negative 1, 3. It's a parallelogram with these vertices. So negative 1, 3. Negative 1, positive 3. 1, 2, 3. Right there. And then 1, negative 3. So to the right, 1. Down, 1, 2, 3. There. Then we have 3, negative 1. To the right, 3. Down, 1. Let me go ahead and label these. Negative 1, 3. 1, negative 3. 3, negative 1. And finally, 1, 5. 1, up 5. 3, 4, 5, up here. There it is. All right, so we have a parallelogram with these vertices. And we're trying to do this double integral over this region. Now, could we do this without a change of variable? Well, yes, if we could look at that as like a type 1 or type 2 region, which I think we could, all right? You might have to break it up, though, because like if you do type 1, where your x's are between two constants and your y's are between two functions of x, you're going to have to split it because you've got like a certain line here, and then below it changes, right? So I just want to say that the amount of time and effort it's going to take us to change the variables right now, we probably could just do this problem. But we want to illustrate the change of variables process. All right, so you've been given the actual change of variables, right? They've been given to us. And these are the change of variables right here. So I'm taking x and I am replacing it with 1/4 u plus v, and then taking y and replacing it with 1/4 v minus 3u. When you look at those transformations, right, we're transforming from x and y here over to some new plane in some new region here where this can be our u variable and our v. What we're hoping is that when we do our change of variables, this shape that's complicated becomes something nicer over here. And so we need to maybe take a look at what it is. And for those of you who've taken linear algebra or just understand the idea of linear versus quadratic, these transformations are linear because u is to the first power, v is to the first power, v is to the first power, u is to the first power. These are linear transformations. And because they're linear transformations, anytime you have a linear transformation, points go to points, lines go to lines. So anything that was a line here is going to be a line over here. Anything that was a point over here is going to be a point over here. So what I'm going to do, now we have to know that, and that's something that you wouldn't know until I told you, unless you did linear algebra or something like that. So I'm telling you now. So these transformations should be linear, and lines are going to become lines. So what I'm going to do is just see if I can map these points over into this plane. So let's start with the point -1, 3. This is our x, this is our y, right? What happens, where does that get sent over here? Well, let's look at our equations. We have x equals 1/4 u plus v, right? And then the other one is y equals 1/4 v minus 3u. So let's see what this point does. X is what, -1? So I'm going to replace this with -1. So -1 equals 1/4 u plus v. And then the other equation becomes 3 equals 1/4 v minus 3u. And I have two equations with two unknowns. And if I have two equations with two unknowns, then I should be able to solve for the two unknowns, two linear equations. So let me do that now. I'm going to solve it. It's like a system of equations. And I'm going to need more room. So let me just erase this. We'll come back to it. So to solve this, I'm going to multiply both sides by 4 to get rid of the fractions. We get -4 equals u plus v. And I'm going to multiply both sides here by 4. I get 12 equals v minus 3u. Let me write it this way. -3u plus v. Is that all right? I changed the order. And then the 4 cleared out. We good? There's my system of equations. So I can solve that system using any method I want. And the two methods that we learn are substitution and elimination. Now, I'm a fan of elimination, so I'm going to do elimination, but you could do substitution as well. Substitution, you would solve one of these for u or v, plug that into the other one, and solve, right? I like the elimination, so I'm going to do, what I'm going to choose to do here is I'm going to try and, go ahead. Yeah. You want to kill the u's off? Okay, I was going to go after the v's, but we can do the u's. I'm going to make the u's go away, so I'm going to multiply this top equation by 3. And that will create a new system, -12 equals 3u plus 3v. 12 equals -3u plus v. So that's just scaling the first row by 3, and then add straight down, and you get 0 equals 4v, but that means v is 0. And once you know what v is, you can go back and get u, right? By plugging 0 into any of these, right? So let's plug in. I like this first equation right here. I want to go back to here. Let's replace v with 0. U is -4. Okay. 1 down, 3 to go, right? We got to move all of these points over. But the good thing is once we move all the points over, we should be able to draw lines, right? And we'll have a good idea of what this region looks like. Okay, now we go with the next one. Unfortunately, I don't have this worked out already, so I'm going to have to go through this all. Otherwise, I just tell you what it is. But it's going to be the same setup, right? I go to the next point, this one right here, and then I do the same thing. So what do my equations become now? X is 1, right? So 1 equals 1/4 u plus v. -3 equals 1/4 v minus 3u. Do y'all see I'm just following that same procedure? Yeah. I'm going to come up with two equations over here. Clearing out the 4 again, you get 4 equals u plus v. And here I get -12 equals, I'll change the order again, -3u plus v. There's my system. Do the same clearing. You want to kill the u off again? You want to do the v this time? Yeah. Okay, we'll kill the v off this time. So to kill the v off, multiply the top one by -1. Is that all right? Or the bottom one. It's up to you. Yeah. -1 on top. So we go get -4 equals -u minus v. Then -12 equals -3u plus v. Add down. -16 equals -4u. So divide, you get u is 4. Is it locked? So if u is 4, what's v? 0. Okay, I got rid of the other one. This was x and y. Let me list them out over here just so I have them. What was the first point I got? We're talking about in the UV plane. I've got the first point was, it was 0. -4, 0. And then I just got 4, 0, didn't I? Okay. Hey, that's good, I think, because those both have the same y coordinate, right? Same y coordinate, different x coordinates, which means they lie on a horizontal line, which already seems like maybe that's going to be a better region. But we got to do 2 more, right? Okay. So now we're going to do the point 3, -1. So replace the x with 3, the y with -1. This is monotonous. I should have had this done before class, sorry. -1 equals 1/4, and then v minus 3u. 3u. 12. So 12 equals u plus v. And then -4 equals, switch the order again, -3u plus v. Your choice. You want to do the v again? Yeah. Okay. Okay, so -1 on top, we get -12 equals -u minus v. -4 equals -3u plus v. Wait a minute. What's that? V is equal to, wait, v's going away, right? So what are we getting here? -16 equals -4u. So u is 4? U is 4, and what is v? V is something different this time.
8.
So u is 4, right? U is 4, subtract 4 on both sides here. 8. V is 8. So 4, 8. The last one. Any questions? Okay. So the last one, we're going to do 1, 5. 1, 5. So 1 goes in for x. 1 equals 1/4 u plus v. And then 5 equals 1/4 v minus 3u. Tedious, right? Shit, we could have, that's what I was saying. We could have probably done this already. But it's more about us seeing this in action. All right, 4 equals u plus v. And then 20 equals -3u plus v. All right, I'm going to multiply both by -1 again. -4 equals -u minus v. 20 equals -3u plus v. Add down, you get 16 equals -4u. You get -4 equals u, which means v is 8. I went quick there, but -4, 8. Okay, there we go. Got it? So what is the transformation of this parallelogram in the xy plane to the UV plane through that transformation? Let's plot these points in the UV plane. May I erase?
Yes, sir.
Everything good? Okay, so in the UV plane, I'm going to put it over here. In the UV plane, we have the UV plane. We have the point -4, 0. 1, 2, 3, 4, -4, 0. we have 4, 0. What? Right, 4, 0, 4. Did I say, yeah, I said horizontal line earlier. Yes, I did. Okay, 4, 0. And then we have 4, 8. I'll put 8 right here, even though it's not really to scale. 4, 8, and negative 4, 8. And look at that. That's like a type 1 region. Or not even type 1, rectangle, sorry. That's a rectangle. This is like the best. This is the best case, right? Through that transformation, we have this. Okay, good. Now what we need to do is transform the integral over. So this integral, the double integral that we had over d of f of x, y, dA, is now going to become the double integral over, let's call this, let me use what I had in the notes. So this is what I had in the notes. When you do a change of variables, your original double integral over d, f of x, y, dA, now becomes a new double integral over s. So s is the region in that new space, right, the UV plane. And then it'll be f, but you got to switch your x's and y's over, right, using your transformation. And then you have this thing, the Jacobian, right? So let's see if we can't plug that in. Let me go back to my example here. It was the original one. Let me just put it next to it. It was this over d of 4x plus 8y dA. Okay, so for us, that's now going to become, yeah, using that, this is going to become the double integral over s. Okay, 4x times 8y. All right, but 4 times x, what was x? I erased it. It was 1/4 u plus v. So what's 4 times 1/4 u plus v? It's just u plus v. So we get u plus v. Okay, plus 8 times, and the other one was 1/4, and it was v minus 3u. So what happens, that's what y was, right? So hit that with an 8, and you're just going to become 2 times v minus 3u. Distribute through? 2v minus 6u. 2v minus 6u. Are you all clear where I'm getting that from or no? Yep. You sure? Everyone's good? Sure? That's just this, right? Replacing this, plugging the x, y transformations in to the function. Now I need that. So magnitude. Yeah, I should have just wrote these down. Let me write them. Just have them on the side here. So I may have told you all this already. When I was a student, I had a lot of trouble seeing the difference between the U and the V for myself, with my own handwriting. So I had to adapt my handwriting. And that's why when I do a U, I always put a little curl on the end of it. And when I do a V, I try and like arc the second part of the V over and really make sure I have a point there, but not so much that it looks like an R, you know what I mean? So anyway, all right, here we go. So we need the Jacobian, right? Yeah. The Jacobian. The Jacobian is going to be the partial of x with respect to u. So come over here, take the partial of this with respect to u, which is? So you can ignore that, right? That's going to go to 0. What's the derivative of u with respect to u? 1 times a fourth? 1/4. So it's just a constant. 1/4 times. Now the partial of y with respect to v. Okay, this with respect to v. That goes away. 1/4. Minus, right? Minus partial of x with respect to v. 1/4 again. Times, and then finally the partial of y with respect to u. Negative 3/4. Because the derivative of that's negative 3, derivative of that's 0, so negative 3 times a fourth, negative 3/4. Boom, dA, right? Well, we'll put the limits of integration on the next step. But it's still with respect to area. It's just the area is in a different space now. So what do we have here? 1/16 plus 3/16. So 4/16, which is 1/4. 1/4. Which is a constant, right? I can just bring that out of the integral. That doesn't always work. Look, the fact that all we're doing is scaling by a constant is because the transformations were linear. If the transformations are linear, then the derivatives are going to be constants. But if your transformation is nonlinear, like the spherical one we saw last class, then your Jacobian is not going to be a constant. It just happens to be in this case. So going back to this, I'm going to bring the 1/4 we just got out of the integral, double integral. Okay, let's clean this up. This is minus 5u plus 3v. And now, because we are integrating over a rectangle, the order of integration doesn't matter, right? My u's here are trapped between two constants, -4 and 4, and my v's are trapped between two constants, 0 to 8. So I'll just do that order. I'll go -4 to 4, I'll go 0 to 8, and that will force this to be dv du. And that integral should be easy to evaluate. But again, I think we're long ago done if we kept it as a type 1 or split it up into pieces. Okay? All right, I have another example. May I erase? Yeah. I have another example. Yes,
How did I'm taking your faith on this, but how did we know that x equals 1/4 was going to be giving us this?
Yeah. So the great question. Like I gave you the transformation, right?
Yeah.
Like that's not very helpful if you're trying to do that integral. Like how do you know to do that transformation, right?
Yeah.
So the next example is exactly going to address that question.
Oh.
Okay. So what if you aren't given the transformations, right? The integrand itself might clue you in to an appropriate transformation. Remember, linear transformations take lines to lines. So here's an example, and this is actually the last example of the section, where you have this double integral, right? That's a little too big, huh? Don't need that much, do you? That okay? Can you all see that up there? Okay, let's see why this problem can't be done doing it like we need a change of variables, all right? Let's see why. So let's look at the vertices of this first. The vertices here, we're in the xy plane. 1, 0, no problem. 2, 0, no problem. 0, -1, no big deal. 0, -2, no big deal. These are the vertices. And I would say that's actually not bad in terms of like, it's not a type 1 or 2 unless you split it up, right? But we run into that same thing. Like we could go just that part right there would be like a type 1. And then we could do this part, it'd be type 1 as well. Do y'all agree this is probably doable? Yeah? Doable? So let's try and do it. Let's not use change of variable, and you'll see right away we're going to run into a problem. Because if we try and do this integral, let's not even try and set up the limits of integration, type 1, type 2. Just think about what you would need to integrate that. If you had to find the antiderivative of this with respect to x or y, how would you do it? Do you see the challenge? If you try and do that with respect to x, you have x's both in the numerator and denominator here. With respect to y, it's in numerator and denominator as well. There's not an easy way to integrate this. So in this problem, the thing that's making me think more change of variables isn't the fact that I want to make that a nice region. It's that I can't integrate this. All right? In fact, let's go to Wolfram and have it integrate that. How about that? See what it does. I'm curious. Wolfram. All right. So how about we do, you want to do just the indefinite integral, right? Clear this out. Let's do the indefinite. Let's do e raised, can we see that enough? Okay. And then it was it x plus y?
Yeah.
Over x minus y?
Yep.
Okay, x plus y over x minus y. And you want to do that with respect to x or y first?
X.
X, it wouldn't matter, right? They're both about the same. What do you think? Is it going to be bad? Oh, shit. Yeah, that's bad. That's bad. This is it. And it has this thing in here, EI. What the heck's EI? EI is the exponential integral. So this is really Wolfram Alpha's way of saying, sorry, I'm no help to you, right? Because it's involving other functions that deal with this sort of situation where we can't integrate in a closed form. So there's trouble, right? Now we're going to get an answer, okay? We're going to get an answer, but we're going to have to do a change of variables, all right? Because that integral is not possible for us. Should we see it with respect to y, just in case? Maybe with respect to y was better? Oh, well, no, not xy. Shit, that's real bad. What the heck? I'm sure we're going to get the same thing. Yeah, it's there still, right? So Wolfram has submitted. All right, let's do our change of variables. But we're not given what to do, right? So I'm just going to take kind of a guess at this. I'm going to kind of take a shot. The problem that I'm having with this integration is that my x's and y's are appearing both the numerator and denominator of that exponent. It'd be better if they were completely separated from one another. So I'm going to let the top of this be u and the bottom be v. And just see what happens and hope for the best. All right? I mean, honestly, because there's no guarantee it's going to work. I mean, I know it's going to work, but like if this was the first time I were doing the problem, I don't know if it's going to work. Okay, so I'm going to just say, let u be equal to x plus y. Let v be equal to x minus y. Now, what's nice about the formula this way, like if you notice the previous example, it was solved for x and y, wasn't it? Here, it's solved for u and v, which makes the conversion really nice because these points, right, this was 1, 0, this was 2, 0, this was 0, negative 2, this was 0, negative 1. So in our new plane, in the UV plane, this transformation should go nice. I'll do it here. The point 1, 0 in the xy plane, what does that become in the UV plane? So if x is 1 and y is 0, u is 1. If x is 1 and y is 0, what's v? 1. See how much easier this is? Because these are solved for u and v? The problem is going to be when we take the derivatives. These aren't solved for x and y, so we're going to have to solve them for x and y. But we'll get to that when we get there. Okay, now let's take 2, 0. Where does that go to? 2. And for the x, and then the y goes to 2. 2, 2. All right, now let's take 0, negative 1. So what happens for this one? Negative 1. And then our v is 1, positive 1. And then 0, negative 2. So our u is negative 2 and our 2. Okay, everyone understand we're just switching those over? Let's draw that over here. 1, 1. 2, 2. Negative 1, 1. Negative 2, 2. All right, well, it's not a rectangle, okay? It's not a rectangle. It's not a rectangle. But I would argue it's better than this was, because this would be what I would consider a type 2. Because you're not, can't say y's. It was y's, right? Now it's what? V's are stuck between 1 and 2, right? And our u's are stuck between two functions of v. So it's type 2. So we should be able to handle that, right? But that wasn't even the thing I'm worried about. And this part right here, the fact that it's not that great, it's not perfect, is not the issue. The issue is that I couldn't do that, so. All right. I think we're ready to try and start setting this up. We've got to get the new integral set up. And to do the new integral, let's start it, okay? Let's start it. We're going to have the double integral over s. This is s. We're going to have e to the, and this is the nice part, e to the u over v. And then I need my Jacobian in here, right? Jacobian and then dA. So we need to figure out this Jacobian. The Jacobian, put it back up here, partial x with respect to u, right there. That's our Jacobian, right? The problem here is that this right here, this is solved for u and v. We need x in terms of u and v only, and we need y in terms of u and v only. So I'm going to have to do some work right now on this before I can actually take these derivatives. So where shall I? So right now, I'm going to say question mark here. Let's go ahead and erase this one. And you know what? I'm going to erase this one too. I can draw that pretty easily. You'll help me, right? I'm going to erase that too. All right, so I have that u is equal to x plus y, and v is equal to x minus y. It's just a system of equations. How could we go about doing this?
We could add the two together. That would cancel out the y.
You could add them right now?
Yeah.
That's an interesting approach. I like this. So add these together, you would get what? U plus v equals 2x, and then divide both sides by
So you get 1
2?
half u plus v.
1/2 u plus v is x. Ooh, I like that. That's real nice. So we get an equation for x, right? Okay, then we could have start that over again. You did that, when you did that, you killed the y's off, didn't you?
Yes.
So why don't we kill the x's off this time? I think that's where you're going with this, right? So now -1 through here. And when we do that separate, we're kind of restarting in separate idea here. So this becomes -u equals -x minus y.